This talk grew out of some discussions that Mike and I had back in August about the Platonic space idea and the relationship between math and experience in general. And so, what I would like to talk about today is that issue of how mathematics relates to our experience. And if I understand the Platonic space concept, it looks roughly like this, that there's some domain of Platonic forms or mathematics living in some abstract space that affects the physical world causally, logically, as a constraint, as a set of possibilities. But whatever we want to consider under this term ingression into. And then the physical world has some causal effect on our experienced world. And from our experienced world, we can abstract back to this world of mathematics. And what I'd like to do is just change the emphasis on this picture a little bit and relabel some of the arrows and look at it this way from the point of view of the experienced world. And I'll argue that we can also run this cycle with these labels on the arrows, that in fact our experienced world actually defines mathematics or can be viewed as defining mathematics, which describes the physical world, and the physical world writes data to our experienced world. So this is a very specific idea of causation. So this way of kind of rewording things was motivated by this question of what sorts of systems can we expect to have the same math that we have? And this, of course, rises in things like the question of identifying non-human civilizations or SETI and all of that. Messages have been sent on spacecraft that encode various kinds of mathematics in the hope that if anyone ever found them, they would be able to understand the math. And that makes the assumption that any kind of culture that would know how to deal with a space probe knows enough mathematics to figure out what we're trying to talk about. So this is kind of a live question of who has the same math that we do. And clearly on the Platonic view, everybody does by definition, because mathematics is completely independent of experiencers. It's independent of observers, it's independent of the physical world, it's independent of everything, basically. Well, we can only find out if some other system has the same math that we do if we share communication capabilities of some kind. And of course, the SETI assumption is that that mathematics itself becomes the shared communication capability, up to questions of encoding and language and that sort of thing. Now, the alternative view that I want to suggest we can take, which I'll call the experiential view, is that systems will have the same math that we do if they have the same general kinds of experience that we do. And in that case, the communication capability follows from the shared experience. And I don't think that these two ways of thinking are different on any facts. I don't think there's an empirical difference between the two. I think it's a difference in perspective. So what I want to see in this talk is what we may be able to learn or understand from this different experiential perspective on math. So where we're going is to talk about experience a little bit, to talk about how very general properties of experience relate to very general properties of mathematics, and in particular, very general properties of categories. which are the most general kind of mathematical object that we've got, at least at this point. And then talk about some examples of getting from categorical math to math as we know it. Discuss proof theory and logic a little bit. Talk about why math is both hard and, in a sense, very natural. And then kind of summarize what perhaps we can learn from thinking in this way. And again, I don't think this is factually different from the Platonic perspective, but different in an interpretive sense. So let's go. First, experience. Here are two kind of pictures for thinking about experience. The one on the left is obviously very old and very traditional and was around in Plato's time and well before Plato's time. Appears explicitly in Descartes as a guiding feature of the whole kind of modernist viewpoint that grew out of the Enlightenment and lasted, is still very current today. I think if you ask most people to describe experience, they'll offer a picture something like this. On the right is an alternative picture of experience that comes fairly naturally out of physics. If you take a very fundamental physical point of view, but interestingly, it's also the point of view that one gets from the free energy principle literature, where the experience world is basically the boundary between two parts of the physical world, one of which we call an observer, and the other of which we call that observer's environment. And they're separated by a Markov blanket or a holographic screen or some sort of boundary that encodes information. And that boundary is viewed in this picture, at least, as encoding what the observer experiences about the world and what the world experiences about the observer, because the boundary is the transmission channel for their interaction. So it's the transmission channel for all of the information that they exchange. And these two pictures of experience, I think, are going to line up pretty well with the Platonic view on the left and the experiential view on the right.
Chris,
So
can I
what's
ask a clarifying question? Sorry.
Yeah.
Same.
Okay, I start. Voice is muted. By experienced world, you mean the process of experiencing, right? So it's like the communication channel, not holding information or storing information.
Well, the communication channel encodes information, but very briefly, right? It depends on the time cycle of the interaction. So by experienced world here, I mean what it looks like when you open your eyes.
Yeah, so I just was wondering whether it's like the experienced world to an observer, like the memory and an observer has found, like the model an observer has built.
Right. Yeah, it's whatever you see when you open your eyes, with whatever processing layer you want to include. So object construction, for example, as we'll get to in a little bit.
And then I think I know what you're going to say based on what you said to Ben. Excuse me. But is what I experience all input, or just input I deem meaningful enough to act upon? So like the difference between the Umwelt, like the carriers of significance in the environment that are important to me, or all experienced input regardless of how important it is to me?
I think that depends on where you draw the boundary between observer and world.
Okay. That's fair. I get you. Okay, cool.
Okay. So based on this kind of notion of experience, we can ask, what kind of experience do we need to do mathematics? And I want to point back to an old book now that Lakoff and Nunez were two psychologists, Lakoff being a psycholinguist in particular, published back around 2000. I don't remember the exact date. But in this book, they they essentially try to offer an embodied alternative to the Platonic view of mathematics. And they claim that mathematics is a metaphorical language, and that the main metaphor in mathematics is bodily motion, or the observable motion of other bodies. But their main claim is that it's motion of your body is what your mathematics is analogous to. And some years after this came out in 2013, I was trying to understand analogy, particularly analogy in non-humans, but then in humans also, in different domains. And mathematics is clearly a very analogical kind of discipline. So I did a brief survey of functional imaging data of people who were doing mathematics problems in fMRI machines. And indeed, what is differentially lit up when people are doing math in fMRI machines is their motor planning system, which is the system that does analogical reasoning for bodily motions. To me, and seemed to confirm this view of Lakoff and Nunez, that bodily planning was somehow underlying mathematical reasoning. And at that point, the sorts of experiments that were available were people doing simple arithmetic, people doing algebra problems, and people doing calculus. And the effect is strongest for algebra problems and calculus, which seems to me not surprising, because there's more sort of sense of motion in those than in simple arithmetic. Just adding numbers is not represented by the motor system. It turns out there's a nice work by Stanislas Dehaene showing that there's a fairly specific representation just for the number line. So what I want to claim is something a little bit more precise and abstract, in fact, than even Lakoff and Nunez did, which is that the experience of identity over time is the key to understanding mathematics in general. And we tend to take this experience for granted. We just assume that things have identity over time, including ourselves. So I'm kind of working by the motto here: don't take it for granted, abstract it, and see what happens. So let's do that and see if we can build some basic math. So, and let's just start with the experiences about objects. We do experience the world as containing objects. So one could also say our experienced world contains objects. So let's just make that an axiom. And so we're going to assume as an axiom that there are objects. And we also have this experience of identity over time. So in our experience, at least, if nothing happens to objects, they stick around. They do have identity, which they maintain over time. So let's turn that into an axiom, that the things that we've called objects, whatever they are, have identity. And so what we'll do is represent that as a map, an identity map that just takes an object to itself. And here we're using this arrow to indicate the passage of time. And that's significant because it actually takes time to think. This object is still here. So our process of thinking takes time. And so this arrow also represents our process of thinking about an object remaining the same in time. So remaining the same as one process, but we can think about other processes. So another deep part of our experience is that objects can undergo various processes of change. So let's just make that an axiom, that at least some objects can turn into other objects or change state in some identifiable way or distinguishable way, so that we think of it as undergoing some sort of process. And again, we'll represent that as a function, or we'll use the word morphism. And again, this arrow implies time. It takes time for something to turn into something else. All but the simplest processes have intermediate states. So if you think of some long process, one can typically find some intermediate in the middle of it that's repeated in some way that makes it salient. So we can turn that into an axiom, that we have little processes, they compose to make big processes. And another experience, which is a bit more abstract, is that the order of the intermediates matter, but it doesn't matter how you group them together, as long as you maintain the order. So we can make that an axiom, that order matters, but otherwise you can think of processes as kind of glomming together into bigger processes any way you want to. So you may recognize these axioms as the axioms of category theory. And here's a formal statement of the axioms of category theory, stated as a definition. A category is a bunch of things called objects. There are things called morphisms between them. Each object has an identity morphism, and morphisms compose, and the composition is associative. And these conditions B and C about the identity operator composing with a morphism doesn't change the morphism, and that the sets of morphisms are disjoint between pairs of objects, are there to prevent kind of perverse interpretations of this formalism. This is taken from a standard textbook. You can find different statements of these axioms in other textbooks. They all give you the same theory. But this is the basis now for mathematics, is this theory of categories. And it captures a bunch of other correspondences that are fairly common life experiences. One is there's usually more than one way to get something done. So if I'm going to grab my teacup over here, I can reach for it in different ways. I can solve all sorts of other problems in various different ways. And in category theory, essentially all interesting categories have commutative diagrams. And commutative diagrams are just depictions of different ways to achieve the same result. In life, some actions can be reversed, others can't. But when actions can be reversed, things are a lot easier, because you can kind of back up and start over, and you aren't penalized for doing something wrong, or at least you're not penalized forever. And in category theory, some morphisms have adjoints, which are basically inverses, generalized in a particular way, and they always make things easier. In life, we also have this fact that the order in which things are done can matter. If I do one thing and then another thing, it's often you get a different result than doing the second thing first and then trying to do the first thing. And in fact, in category theory and math in general, in fact, things that operations commuting is a special case. And when things commute, that makes things easier. But that kind of commuting operation is actually fairly rare, as opposed to a commutative diagram, which is not rare. So the nice thing about category theory is that all the rest of math is just a special case. So sets, groups, rings, fields, vector spaces, topological spaces, essentially any mathematical structure you want to think of is a category. And they differ in specifying different properties of the objects and the morphisms. For example, if you're talking about groups, then the objects are groups and the morphisms are homomorphisms between groups. If you're talking about vector spaces, then the objects are vector spaces and the morphisms are linear maps. But all these systems exemplify these basic intuitions that define categories. Objects have identity, processes commute, and order matters. What these special cases add are different definitions of the elements in an object and various operations on these elements. But to get from category theory to math as we know it, there's really one key intuition. And the key intuition is that composition of morphisms is the fundamental binary operation that gets used in various forms in every kind of mathematical system. Here's a simple case. Suppose we have an object that just has one element, so we can think of it as the object itself, x. And we have some map that takes x to x. So we can obviously apply this map as many times as we want. And we can generate diagrams that represent f or ff or fff or as many f's as we please. And this kind of diagram of composing f with itself looks a lot like concatenation. So it looks like a lot like addition. And it lets us think about, say, the number 1 is do f once, and 2 is do f twice, and 3 is do f 3 times, etc. And in fact, this kind of entity is called a monoid because there's just one object. And you use a structure like this to develop the theory of the natural numbers and in fact, any other kind of number in category theory. So to give you an example of how this works, we can think about how you get prime numbers. You get numbers by doing 1 over and over again. You get even numbers by doing 2. And then if you do other numbers like 3 or 5, if you do 4, you don't generate anything new. If you do 3, you get a redundant copy of some of the things that you got by doing 1 over and over again that you didn't get by doing 2 over and over again. And if you do 5, you get some new redundant copies also. If you do 7, you get some new redundant copies, a lot fewer. If you do 11, you get new redundant copies, etc. And so the numbers that introduce new levels of redundancy are the primes. So to define prime numbers, you just need concatenation of morphisms. You just need composition. You don't need to define special things like multiplication or factoring or that kind of thing. You really just need morphism composition and associativity, because it's associativity that allows you to draw parentheses around things. And what prime numbers really reflect are what happens when you start drawing parentheses around things. So drawing boundaries around sets of operations and considering them to be big operations. So primes are really, really basic things that follow immediately from really simple ideas about what can be done in the world. One of which is putting boundaries around things in your experience. So here's another example. This one from quantum theory. A qubit, a quantum bit, is just an object about which you can ask a yes/no question along some dimension. Is it black or white? Is it big or little? Et cetera, et cetera. Just simple yes/no questions. And a qubit space is a vector space, basically, of those kinds of objects, or as representations of those kinds of objects. And we're interested in those kinds of objects. We're interested in their behavior in time, so we can parameterize this representation by time. And if we do that, we get a vector space of periodic functions. And those things are quantum states. And quantum theory is just the theory of unitary operators on these kinds of qubit spaces. That's all it is. It's actually a very simple thing. And these unitary operators represent time evolution. So You can map a vector at one time to a vector at some other time. And then you can think about asking a yes or no question of that vector along whatever dimension you want. And this gives us an example of, in fact, a way in which math can be misleading. The language is so general and so powerful that it's very easy to say things that are confusing or that build more into a representation than is actually there. And here's an example. You often see qubits represented by these block spheres in three-dimensional space. Now, in essentially every textbook, I mean, this picture is from Wikipedia. And when you look at this representation, you can ask, where do these spatial coordinates come from? What does that have to do with the definition of a qubit? And why are there two angles here instead of just one? When we defined a qubit, we talked about one angle. Here we have two angles. And as it turns out, these X, Y, and Z directions in three space are the three orthogonal ways that we can choose a reference direction Z in the definition of a qubit if that qubit is supposed to represent something that we ask a spatial question about. So in fact, this representation is not a representation of a qubit. It's a representation of our measurement capabilities in a particular special case of a kind of yes-no question, which is a yes-no question about spatial orientation. So here we've developed a beautiful mathematical representation of something, but we called it a representation of something else that it bears a certain resemblance to, has a certain relationship with, but the block sphere is not a representation of a qubit. It's a representation of a bunch of reference frames. So let's look at another example, the example of computing. And I'm surprised that Joshua Grochow didn't talk about this view of computing in his talk earlier, or it was last week. This is a view of computing that comes from a paper by Claire Horseman and all back in Royal Society A in 2014. What they do in that paper is point out that treating a physical system as a computer and treating it as computing some function is exactly the same process as doing an experiment on a physical system and coming up with a model of that system's behavior that's formal and predictive. So this picture shows two models, which I've labeled M1 and M2, that describe some system S and its physical behavior over some time dt. And if M1 may be describing this system S as computing some particular function from some input, some initial state, or some data, and M2 may be describing the system S as computing a different function on different input data. And the input data is just a different interpretation of this initial state. And the answer, obviously, is a different interpretation of the final state. And we might have some theory, some piece of semantics that actually allows us to connect those two. If M1 and M2 are virtual machines running on the same physical computer, for example, that semantic theory is the semantics of some programming language. So in this picture, a physically implemented computation is a commutative diagram. What we require is that all the paths into any given object on this diagram give you the same object. So all the paths are multiple ways of doing the same thing. Now, thinking of it this way actually helps make some assumptions explicit. And that's one of the things that math is really good for. In the computing case, when we make the notions of measurement and interpretation explicit, we learn something. We learn that interpreting something as computing requires computing. So if I'm interpreting some device as adding two numbers, And I have to add two numbers to actually construct that interpretation. So that tells us that we haven't, with this picture, actually defined computation. We've assumed computation. So this, quote, definition of computation is circular. But it also tells us that we can't interpret a process as computing something that's not computable by us. So we can't actually interpret a physical process as computing something that's not computable by, say, a Turing machine, which is our current model of computation. Current model, as Joshua pointed out, of computation by us. This picture also makes it obvious that many interpretations are possible of any physical system. So things like polycomputing and virtual machine stacks and all of that kind of fall out of it as possibilities. And finally, it tells us that computation is relative to environmental constraints because it's the environment that shapes the free energy landscape of whatever the physical system that's doing the computing is. And we kind of tried our best to get around that when we build computers. So we build them out of metal and plastic and stuff like that, and we give them enormous voltages compared to the operating voltages of their components to try to keep them stable. But this notion of computation is relative to environmental constraints that shape the landscape, I think is very important when we think about computation by biological systems. So let's move from the structure of mathematics to its dynamics, if you will, which is the dynamics of proofs. And the proof theory of math is based essentially on first order logic. So the basic components of proofs are these. The first one, of course, is modus ponens. If you have A and A implies B, then you can conclude B. And this rule sort of encapsulates two assumptions that, again, we take from experience. One is that objects do things, they have causal power. A in this proof schema sort of causes B. It causes this conclusion in some way. The other assumption this embodies is that by making this an inference rule, we say that it always applies. It's context independent. So we're assuming a kind of context independence of the causal power of entities when we write down a rule like this. The second line here is the law of excluded middle or double negation. Not A gives you A. And here we're effectively assuming that things are decidable, that we can decide whether we have A or not A. And then the third line just contains the standard quantifiers in first order logic. There exists uniquely and for every is just, there doesn't exist a counterexample. So not exists, not. And what the use of these operators assumes is that membership in classes is decidable. So we can tell whether an object satisfies a predicate or not. Otherwise, these symbols would be meaningless. But context independence and decidability are big assumptions, as we've learned in the 20th century. So you can ask where they come from. And these are deep assumptions of the modern worldview. And they were not really enunciated until we get to the modern worldview. So, for example, Newton limited non-locality, so context effects that you can't see, to gravity. Gravity acted instantaneously, but nothing else did. And Einstein got rid of non-locality altogether. He said, look, all physical interactions have to be local. Information travels at the speed of light or less. So no instantaneous action at a distance. So post-Einstein, so for example, in general relativity, classical physics assumed local context-free events observed by observers who are effectively omniscient, so they can measure things with real numbers. They can do physics in a continuous representation, and effectively omnipotent, so they can isolate systems. So classical physics basically assumed that observers were kind of miniature gods who had incredible power to hold the environment at bay while they did an experiment, and incredible power to measure things, to get real numbers. And these assumptions are built deeply into first order logic, which developed as a formalism at essentially the same time, and so are built deeply into Hilbert's program, enunciated in the early 20th century. And we all know what happened next, right? Gödel's theorem basically proved that in mathematics, the notion of truth involves hidden assumptions. And Turing's theory of computability basically proved that set membership very often isn't decidable. The uncomputable problems can all be represented as decision problems about set membership that are undecidable. And then not until 1969, I think, was the frame problem enunciated. But the frame problem is basically a reminder that context matters, that the consequences of what you do depend on contextual variables that you can't see in principle. So these sorts of things now look inevitable to us, that these assumptions that underlie the Hilbert program and hence underlie first order logic and proof theory don't hold in all circumstances. So proof theory itself has these deep conceptual issues that we only didn't see because we weren't looking at our experience in the right way. We weren't noticing that we don't actually have the sorts of powers that these assumptions make it look like we have. So here's a timeline that just shows some main events between Clausius's first definition of entropy and Friston's definition of the FEP, and Chris Fuchs' definition of cubism, actually. It's about 150 years between those two. And a lot happened in that 150 years that demolished much of the conceptual framework of the classical worldview upon which proof theory is based, and in which the Hilbert program was based. And I think it's hard to view it as a coincidence that Gödel's theorems, quantum theory, information theory, and the theory of computation were all developed in essentially a 10-year time period of massive conceptual change about what formal systems are, and so about what mathematics is. So let's then return to this question of why is math hard, and why, on the other hand, does it seem so natural? So one reason it's hard is that classical physics got it wrong. Right? The world isn't transparent. We don't actually see everything that the world is doing. We have this experienced world, but the experienced world is not the world. It's not the physical world. That was an equality that classical physics made that the last century has just shown to be incorrect. And the other reason math is hard is that Goffey got it wrong. that first order logic is just not a good description of how our minds work. But math is nonetheless natural. And one reason it's natural is that math is about analogies. It's about how different formal systems or different languages are really doing the same thing. And we're really good analogy machines. We're bad at first order logic, but we're good at analogy because analogy is what our motor systems do. And it's what the motor systems of all animals do. It's how we manage to achieve the same goal by multiple means when that goal is in the physical world, the world of bodily motion. Analogy is why we can take multiple paths to an answer. So here's an example of why math is hard. This is an example of non-transparency. Mike sent around a paper a week or so ago about geometric phase, which is a really new concept. It didn't develop until the 20th century, and its full development by Berry, I think, was not until the 1990s. But when we think of experience in the way that was on the right in that early slide, we can understand why things that we experience just in general have geometric phases. We're experiencing the actions of a very high dimensional environment on a low dimensional boundary. Our experienced world is a low dimensional structure. It has to be low dimensional for us to be distinguishable from the environment. If the dimension of the boundary was equal to the dimension of us, we'd be entangled with our environments. So we experience this low dimensional projection or action of the environment on our experienced world. So dynamical paths in the environment are almost inevitably going to be mapping many to one to paths in the boundary. So what we see in our experienced world is ambiguous between different ways that the environment is behaving. And that's what geometric phases represent. The distinction between paths in an experienced set of measurements and paths in some process that's causing those measurements. And computers are the perfect example, right? If you type a cycle like ls, then you're going to get the same answer. If you type a cycle like ls rm star dot star ls, you're going to get a really different result. That's a geometric phase. The computers are useful exactly because they have lots of internal states that we don't watch all the time. If we had to watch them, we might as well do the computation ourselves. So we have to look at them to interpret them as computing, but once we're done with that, we just let them do their thing, and we trust that they're getting the right answer. And we check now and then to make sure, but that's very laborious, and in most cases, it's not even feasible for the sorts of calculations we like to do now. Here's an example of why math, in a sense, is easy and natural. And this is the definition of a functor, which is just a map between categories. And a functor is a map between categories that preserves the essential categorical structure. So in particular, it preserves composition of morphisms, and it preserves identities. Now, these are exactly the requirements that Dietrich Gentner, who's a psychologist, came up with studying the structure of human analogy making. So functors are just well-formed analogies between mathematical systems. And like analogies in general, they can preserve more or less information in addition to this basic category theoretic information. So I can have a functor that forgets a lot of things, like mapping groups to just sets of elements, forgetting all the group structure stuff. Or I can have functors that preserve a lot of information, that show that two different categories described in two different ways are actually exactly the same thing. And lots of interesting results in mathematics are descriptions of that kind of functor. So earlier this year, there was a great announcement of the solution of a large part of, God, I've forgotten the name right now. I'm sorry. Oh well, it'll come to me. The grand program of trying to associate essentially number theory and geometry. And
It's the Langland program.
Langlands, yes, I'm sorry, the Langlands program. And this is exactly demonstrating a very detailed analogy that we didn't know existed. We thought maybe it existed. Langlands proposed that it existed, but it required a huge amount of work to actually demonstrate that analogy between different formal structures. So functors are representations of analogies. And semantic maps are functors. So a well-defined semantics is just a useful analogy. And I'll point here to a beautiful paper by Joseph Goguen in Mathematical Structures in Computer Science back in 1991 called The Categorical Manifesto. And here Goguen basically argues that category theory is the most natural possible language for understanding computer science, including things like semantics of programming languages. So what are we doing when we're doing math? We're constructing very carefully defined analogies that allow us to explore the space of possible semantics or interpretations of different sorts of systems that behave in the way the systems in our experienced worlds behave, that behave in the way that respects the axioms of category theory. So when we're doing math, we're basically playing with language to find a useful description of part of our experience. And certainly from a free energy principle perspective, this is all in the service of active inference, of understanding and modeling what our environment is doing to us, and how we can act on our environment to get it to behave in a way that we like. And I think we can also, from this perspective, answer Wigner's question about why mathematics is so effective. He called it the unreasonable effectiveness of mathematics in a paper in '61, I think. In terms of this picture of observer-environment interaction via a low-dimensional interface. And what this picture tells us is that our environment is basically the same kind of entity that we are. So it's not surprising that our processes are analogs of its processes. And if you think particularly through the lens of the free energy principle, then we and our environments are constantly doing active inference on the same boundary, and so on the same data. So it becomes very clear that what we're doing and what it's doing are actually analogous computational processes working on the same data. In fact, with the same goal, which is preserving the integrity of that boundary. That's what every agent, active inference agent, is trying to do all the time. So let's go back to this question of who has the same math we do. And I think the first most obvious answer is that our environment has the same kind of math. because it's actually a system in many ways just like us. So any system we can observe has the same kind of math. And our mutual observation is a communication process. So from this, I would propose that the Platonic realm that we're looking for is just the world, including ourselves. So with that, I'll stop and say thanks and ask for questions.
Super. Thanks, Chris. Anybody else questions? Comments?
Can I ask a question about your final conclusion? Because in the real world, there are so many things that is very complex, and people are feeling very hard to use pure math to describe. But we are abstract the real world to some very simple abstract math. So I want to know, what is the gap between the reality and the math? Because I do feel there are so many things that can't be or can't easily be described by math.
Well, at least in this free energy principle kind of picture, the main thing we know about, we know basically two things about the environment, at least from that perspective. One thing that we know is that its dimensionality is much, much larger than the dimensionality of our experience. So hence the issue of geometric phases and so on. The other thing we know about it from a free energy principle perspective is that it's an active inference agent, so it's doing Bayesian satisficing. And so its dynamics can be represented as the construction of a predictive model of its environment, and its environment is us. So, but other than that, all we know about it is the evidence that we can get from what it does to our boundary. So what it does to our experience, which is much simpler than it is. And our math is a description of our experience. And so we can abstract from our experience to a model of the environment, a model of the environment's causal processes. That's our generative model in Friston's language that tries to predict what the environment's going to do to our boundaries next. But given the dimension difference, the chances of that model being accurate, if you will, are vanishingly small. So the environment is always surprising us. And conversely, we're always surprising the environment because our dimensionality has to be much larger than the dimensionality of our experience also.
Maybe my question can be rephrased in a different way with some concrete example. For example, people are using very large model to predict a human language or next token. So I wonder, do you consider such large models as a mathematical model of the language, or because I feel it's quite different in terms of complexity if you compare to other like physical laws?
Oh yeah, absolutely. Right. I think of an LLM as a statistical model of a large corpus of language use. So it's not, at least as I see it, a model of language, but rather a model of many instances of language use. And I suspect that our own language capabilities bear a lot of resemblance to that our own language capabilities are less models of language than models of language use. And given the way we learn language, for example.
Okay, yeah. I just struggled with the complexity of the model because some model can be very simple and intuitively many people when many people talk about model, they're referring to some very simple one, but like large language model is a very complex. I don't know if we should we consider it as a mathematical structure or just something that does our task.
Well, yeah. And in a sense, a formal model or a mathematical model of any complex system that is at all predictably useful is going to be, in many cases, infeasibly complicated, right? I mean, you start to have these enormous state spaces with very complicated dynamics. And so I think our notions of what a model is are still attuned to, the motion of billiard balls on a table. We still think of these very simple things. When you think about the computation required to, analyze data coming into one of the detectors at the LHC, and it's a computational process, but it's incredibly complicated. It's probably simpler than an LLM. I don't know.
Thank you.
I have a question about how people try to interpret quantum theory, quantum mechanics. I'm not an expert in it, but I think it's notorious for being very hard to interpret. Even the best experts just say it's a pure mathematical structure. We don't understand it. Is that because the whole notion of identity, that's primal to our experience, which we then translate into mathematics, kind of dissolves in quantum theory because it's uncertainty that's at the core of quantum theory, right? If I understand it correctly, is that why it's hard to interpret quantum theory or at least map it to our experience?
Yeah, I think that's a very fair thing to say. That I think quantum theory fundamentally tells us that there's not that we can't describe the way the world works in the language we use to describe our experience. So, the quantum theoretic description of the way the world works is unitary operators in some big Hilbert space, all of which are purely time symmetric, which doesn't really correspond to anything in our experience. And what's changing when such an operator is acting is a phase angle or a multidimensional phase angle that's not observable in principle, not an observable of the theory in principle. And I think that the person who actually saw this most clearly was Niels Bohr. And probably the person who sees it most clearly now is David Mermin. But what Mermin came up with, and this was in a beautiful paper called Making Better Sense of Quantum Mechanics in 2018 or something like that, was the claim that quantum mechanics really is a theory of personal experience. And this is the line that Chris Fuchs took in Cubism, and Mermin is just expanding on that. Yeah, it does change the picture. It throws the kind of the core of modernism out the window.
Thank you.
I'm sorry. I have a question or two questions. The first question is, so beautiful talk. I'll probably need to watch it again. What about things in our world that are disconnected causally? How does this fit into the framework, basically, that the environment and we are in this dual state that we kind of try to maintain our boundaries, but there's also boundaries which are kind of disconnected. And if you think about black holes, right, from our reality.
What do you mean by a disconnected boundary here? I'm not sure.
The boundary is not disconnected, but the matter within the black hole is disconnected, I think, causally from our universe, right?
Oh, okay. Yeah, thinking about something like, yeah. What we see in that case is information escaping as Hawking radiation. And we don't have a causal picture of how that relates to the dynamics inside. And there are these notions of entanglement wedges and things like that try to represent the information encoded by the Hawking radiation as information about the entanglement structure inside the boundary. But we don't have anything to compare that to. We have no way to identify or measure the entanglement structure on the outside that would correspond to that structure on the inside. Right? We can't say, oh, this particle that was emitted 1,000 years ago is the entanglement partner of this particle that was emitted now.
Okay. And something else regarding, I've been thinking about a similar paradigm actually recently, about Kolmogorov complexity as a measure for intelligence. This often kind of entails that you need an interpreter, right? So you want to find a short program which gives you a certain output, or actually the shortest program which gives you an output. And this is often kind of considered as a measure for how intelligent the system is eventually. Do you think math is the ultimate interpreter in our universe?
Oh, that's an interesting question. I've been trying to understand what mass was for a long time.
Yeah, because this kind of would entail that I mean, if we are now capable of abstracting math in our cognitive machine, and plus we are capable of forming models.
Right. I'm sorry. I heard the word math as mass. I've been trying to understand what mass was for a long time too. So yeah.
Yeah, that's true. Yeah, I need to work on my pronunciation. It's kind of a weird situation that if we try to model something, if we do science, we kind of need to get into this process to understand it, to find analogies. And we also have this ability to run math in our cognitive machine and kind of align this. And it turns out that math is unreasonably effective in our universe. So I wonder whether there's a connection to Kolmogorov complexity there when we do math, actually. Because it's kind of the substrate on what the universe runs, roughly speaking.
Yeah, that's a very interesting proposal. I guess it what all would one be measuring when one tries to measure the Kolmogorov complexity? So the complexity of the axioms can be very small. The complexity of a proof can nonetheless be incredibly complicated, incredibly large. And which always raises the question of, and mathematicians are often looking for, is there a simpler, more transparent proof of this thing? You know, why is the proof of Fermat's last theorem so complicated. I think that makes many people uneasy that proofs that look like proofs of things that can be simply stated turn out to be incredibly complicated and end up making excursions into domains of mathematics which seem to bear no resemblance to the domain in which the problem is stated. Which is, I think, which is part of what underlies the Langlands program, which I don't begin to understand in any technical way. Is this question of why do we have to make these huge excursions into domains that look like they have no relevance to the problem we started out with in order to solve this problem? And that seems to be the only way to solve it.
Yeah, that's a good point. Yeah, thanks for the talk.
Thank you. Thanks for your question.
I think I need to hear this lecture again before asking more questions.
So I just want to follow Ben's question because column graph complexity reminds me of Hawking problem that ideally or conceptually we could consider some program that doesn't end at all. But in the reality, we seems in the physical world, there's no definition of start and end. And I just want is so if you consider mathematical form is rooted in physical world, how could we get the concepts like infinity and halting or non-halting problems?
I mean, I guess I would see both of these as questions about limits or limiting processes. And the notion of a limit is always a notion of some maximal or minimal entity that might exist, and proving that such things in fact do exist can be very difficult. So the abstraction itself, the concept itself, is built very deeply, in fact, into category theory. There's a general definition of a limit and its opposite, a co-limit. Again, turning those into concrete things, demonstrating in a particular case that this, in fact, is such an entity, can be very hard. I don't know whether that completely addresses the question, but this maybe one would want to call it an imaginative abstraction. This thing might exist. If it does exist, it has these properties. It's kind of what we're doing when we're imagining these limits or co-limits.
Yeah, exactly. That's what I want to ask, like how some imaginary things can exist in our concept, why it not exist in the real world.
I think this is because we are such good analogical reasoners that we can construct a scenario that has some features of something we've observed, but not all of them. So we can We can construct the idea of a process, for example, that doesn't stop. It has all the features of something we observe, except the idea that there's at some point that we see it halting. And a lot of what we do observe in the world at least appears to be perfectly periodic. So the diurnal cycle, for example. And once you get Newtonian physics, you think, okay, well, the diurnal cycle will end sometime, but it's a long, long time in the future. So we have these cyclic behaviors that at least look like they aren't changing at all. And that may give us some reason to imagine that there are lots of things like that. I mean, I think you're asking a question basically in evolutionary psychology here.
Yeah, maybe. Yeah, because I could feel this. One of the explanation is like phenomenological explanation is we prefer some simple explanation, but I just don't know why we prefer simple things.
Well, I think one reason we like simple explanations is that they're actionable and they're easily actionable without spending a lot of energy. And we want to know what to do, right?
Yeah.
It feels uncomfortable when the simplest explanation is very complicated.
Chris, could you do me a favor, go to the first slide? Because I think it was the first slide. Yeah, that's good. That's that right there. What would you say? And I don't really know if it matters, but I'm just curious. If you were to try to classify this picture according to the sort of standard philosophical categories or attitudes towards the role of, well, I don't want to say observer because it's more than that. The role of primary experience, the kind of thing that Chalmers and others focus on as consciousness or whatever. Like from here, it sort of looks like it's primary. Am I reading that correctly? Or do you think it's constructed, or where would you put this in the standard taxonomy of views?
Yeah, that's a good question because I don't really understand this notion of primary experience. I've never quite understood the notion of qualia, for example. Because we typically we don't experience what used to be called sense data, right? We experience objects and properties and motions and things like that. I'm very interested in, for example, the distinction between, in phenomena like blind sight, which point to the distinction between motion processing and property processing, and this ability to, how we define objects, that we define objects first by motion, and then we layer on these features like color or shape or size or something. And they're nice experiments with visual motion, showing that people track object identity even when all these surface features are changing up to a point, and then they quit doing that. So what's the primary experience in this case? It seems to be the experience of motion, of which we're, in a sense, only minimally conscious, which is why blind sight is such an interesting thing. Right? People can be seeing perfectly well in the motion channel, and that's all actionable. but they don't experience it as vision. It's a complicated way of saying I don't know the answer.
Yeah. Also, one other thing, I wonder if you know the answer to this. How close are we to? So here's what I'm always amazed by in math. It's like you start out with some very basic assumptions. So whether that's set theory or logic, or in this case, what you just showed today, and then eventually you get sort of saddled with some very specific outcomes, like the exact value of E, for example. It's not 7, it's not anything else. It is what it is. And you find out, and to me, it seems like you got out more than you put in some interesting way. Now you could say that, well, it just looks like it's more because it was really sort of latent in there or something, but that close enough. That's basically what I'm saying anyway. So I'm just curious, the project of starting with the kinds of axioms you showed today and getting from there to some of these other sort of facts that crop up, like the value of E, or some of the truths of number theory, or these weird things about packing in different dimensions, whatever. How close are we from actually being able to construct those things from the axioms that you showed? Is that something I assume people are working on? Is it going well? How's that looking?
I'm not quite sure how to answer that either. I think operationally, and this is only my impression since I'm not a mathematician, the main use of category theory is to show that different mathematical problems are notational variants of each other. And by showing how the systems in which the problems arise relate to each other as categories. And this, for example, is what the Langlands result is about. It's showing that two different problems are effectively notational variants. So it's constructing an analogy that's precise. So I don't know in what sense one would say one starts with, say, the axioms of category theory and tries to derive the value of E, other than one starts with category theory. One defines the complex field, and one uses geometry and the complex plane to define E. I think those are the same process.
Isn't that kind of what Principia Mathematica is supposed to do? That logic underlies mathematics, and everything about math actually comes from logical axioms. Bertrand Russell's work.
Yeah. I would say, this is, it's in the same tradition of trying to find a foundation for mathematics that works and that is useful.
Got it. Okay. Anybody else?
Yeah, Chris, I have a question about slides 2.
Which is the next one.
Oh, sorry, the next one. So do you think that the arrows could also go the other way? So that the experience world writes data into the physical world, and that the physical world describes the Platonic space that again defines the experienced world. So that it's a loop that goes the other way. Because I'm wondering if, yeah, sorry, that's the question.
This is a very category theoretic type of move. What happens when you reverse all the arrows? Do you get the same picture? Yeah, I love that. It's a wonderful question. Certainly in this free energy principle type of view, the part of the physical world is always sending information to another part of the physical world, and it sends it through an experienced world. So information is flowing through the physical world, or is flowing from the physical world through the experienced world back into the physical world, just a different part of the physical world. So yes, the experienced world is writing in the physical world. The physical world could, I think, clearly be thought of as a model of the formal world, right? In the same way that a physical computer is a model of a function. A physical computer that's doing something is a model of a function, a physically implemented model of a function. And I think you could reverse the defines arrow also if you wanted to, and say that our experience world is also a model of some formal structure, in that what we experience are objects and relations, and objects and relations can be considered formal entities. So yeah, reversing all the arrows seems to work just fine.
Yeah, I'm wondering if the experience world leaves vibrational traces in the physical world that stores like past memories in the Platonic realm that are waiting until present patterns are ready to be to recognize old patterns again. So, for example, the dinosaurs lived millions of years ago. Before a long time, the information of the dinosaurs didn't exist in our physical world until the current experienced world was ready to recognize its information with new tools and was ready to draw the information back into our world when we had the right tools and the current experiences to recognize that information again. So I feel like it's a loop where old patterns are continuously waiting until present patterns are able to draw it back in.
I think that's a perfectly reasonable way to think. Yeah, I mean, in a sense, I would say in a deep sense, this notion of geometric phase is, in a way, a formalization of what you just described. That there may be very long-term cyclic behavior in the physical world that reflects very ambiguously into the experienced world, or the world of experimental outcomes, let's say, is the experienced world. We see what appears to be cyclic, maybe, in the experienced world, but what's going on in the world that we're probing, the physical world, is much more complicated than a simple cycle. and can store a lot of memory. It's very history, can be very history dependent.
Okay, anyone else? Okay, I think that's it. Thanks. Oh,
Yeah,
go
sorry.
ahead. Go ahead, Lou.
So you mentioned at the end of your talk, so the seminal text of the unreasonable effectiveness of mathematics in the physical sciences. And recently I saw also there's a paper from Stuart Kaufman, which is a bit provocative. He's saying the title is The Reasonable Ineffectiveness of Mathematics in Biology. And do you think, so he's basically arguing that we are a bit reaching the limits of mathematics in biology. And do you think it's true, or do you or that we need a new kind of math in biology?
I seem to recall seeing that paper by Kaufman, but I can't recall any of the details. I know, for example, that he often talks about the inability to define state spaces or to represent state spaces with the amount of information available in the universe or something like that. But it doesn't seem to me that limitation on explicit representation has anything to do really with the abstract concept of a state space. And to some extent, I think the question becomes, what are we trying to do with mathematics and biology? Right? If our goal is to build an exact simulation of a human being at molecular scale accuracy, then this isn't feasible even with the classical physics description, and it's not possible in principle with a quantum theoretic description. But is it even a sensible goal? Does it make sense to talk about that? I mean, I know that people that talk about, uploading your consciousness into a computer talk about just that sort of thing. And that sort of discussion seems, quite frankly, to be crazy to me. But I think we've just scratched the surface of actually using mathematics in biology, that there are all manner of kind of available mathematical structures that we tend not to use or to use very much biological thinking. So there may be many things that are useful that haven't, in fact, even been explored yet. But it requires asking the right question and having the right kind of goal. And I think this goal of perfect simulation is actually not a reasonable goal.